We're going to talk about chords and arcs today. A chord is a segment whose endpoints are on the circle. So it's the lighter blue line. And then we've also talked about diameters, arcs, and tangent lines. Now, we're going to look at some theorems about circles. So the first one is, within a circle or congruent circles, congruent central angles have congruent central arcs. And the reverse of that is true. If there are congruent arcs, they have congruent central angles. So if I know the central angles are congruent, then I know the arcs are also congruent. Circle theorem 2 says, within a circle or congruent circles, congruent central angles have congruent chords. And the reverse is also true. If they're congruent chords, they have congruent central angles. So if I know the central angles are congruent, then I know the chords connecting the endpoints, or the intersections of those lines, or the intersection of diameters, the chords are going to also be congruent. And the reverse is true. If the chords are congruent, the central angles are congruent. The second one says, within a circle or congruent circles, congruent chords have congruent arcs. Or the reverse, if there's congruent arcs, there's congruent chords. So if I have congruent chords, I also have congruent arcs created by the division of those chords. Circle theorem 4 says, if chords are equidistant from the center or centers the center are congruent. Within a circle or congruent circle, chords equidistant from the center or centers are congruent. And the reverse is true. Chords that are equidistant from the center or centers are going to be congruent. So if we have chords, we know they're equal distance from the center at a perpendicular angle, because we always measure distance at a right angle. And I apologize for the confusion. Please read that again. It says if the chords are congruent, then they're equal distance from the center. 5, 6, and 7 all kind of run together. It says, 5 says, in a circle, if a diameter is perpendicular to a chord, then it bisects the chord and the arc. So if we have a diameter, we know it bisects the chords and the arc. Circle theorem 6 says, in a circle, if a diameter bisects a chord that is not a diameter, then it's perpendicular to the chord. So if we have a diameter that bisects the chord, we know it is going to be perpendicular. And in a circle, the perpendicular bisector of a chord contains the center. So if we know a line perpendicularly bisects a chord, we know it's the diameter or contains the center of the circle. I know that's a lot of theorems, but we're going to look at some examples of how this is useful. So we know because those chords are equal distance from the center that they're equal. So I can set 35 equal to 6x minus 7 and solve for x. X is 7. In the second one, I know because it's a diameter that's perpendicular, I know the arcs are going to be congruent, and so we set the arcs equal to each other and solve x is 7. And the second one, I know that the parts of the chord are also going to be congruent because it bisects both the arcs and the chord. So we set y plus 4 equal to 2y plus 1 and solve. We get y equals 3. Find the length of CD, which is a right triangle, if you look at that. So we're going to call CD x to make it easier. We're going to use the Pythagorean theorem. 25 is the hypotenuse. 7 is one of the sides. So we're going to get x is 24, or CD is 24, because we know it's a right angle. And that's it. I know there's a lot of information in there, but the best thing to do is look back at the examples and see how this is actually applicable. Have a great night.